Hello, everyone. I think we'll go ahead and get started here. It's about 1 minute past 30 after, so, and seems like most people are logged on. So it's my pleasure today to introduce Tassew Mekuria, who's our next speaker in our series of Maryland Sea Grant Science Policy Fellows. Tassew joins us with a very highly varied and impressive background, both in and outside of research. So he spent a number of years as a high school teacher, prior to researching, and during his doctoral work and master's work, he spent a number of years as a crime scene investigator for the Baltimore Police Department here in Maryland. Tassew joins us with both a master's and a PhD from Morgan State University. For his master's work, he focused on biodegradation and bioremediation of toxic and persistent soil contaminants. And for his PhD, associated with his PhD work, which he'll talk about here today, he's been working on developing all sorts of new methods for detecting heavy metals in water sources. So we're really lucky to be here for this talk today. And with that, I'll let you take it away, Tassew.
Thank you so much. You hear me well? All right. So, thank you, Dr. Richardson. So, as you said, I am in a multi-disciplinary research for the past 5 to 7 years, doing my master's and my PhD. Right now, my assignment is for the University of Maryland Center for Environmental Science, President Office, and reporting for Dr. Peter Goodwin. And I am really supported and in the program of Maryland Sea Grant College. And as you know that Maryland Sea Grant is part of the university system of Maryland that plays an important role in the network or organization working to preserve and the restoration of the Chesapeake Bay and Maryland's coastal waters. And so I am Maryland State Environmental Science Policy Fellow. So today I am going to talk about carbon nanotubes and the cobalt ferrite composite as a nano sensor for monitoring chromium in water. So what we have here is the carbon. We know carbon, when it's combined with oxygen, it forms carbon dioxide. Okay, and when it combines with hydrogen, it forms methane. Both carbon dioxide and methane are greenhouse gases. So as climate scientists, they are considered as something which are bad, right? But when carbons aggregate to themselves, that is the beauty of carbon is that carbon can form a reaction with itself. So carbon to carbon bond forming the carbon nanotubes. And the carbon nanotubes are very important materials in research. So today, most nanotechnology uses carbon nanotubes. And the sister compound, which are known as cobalt ferrite composite, sometimes known as CFO, are also a best candidate for many researchers in sensor or any other application in the nanotechnology. So today I'm going to combine these two substances together to detect heavy metals in environmental elements such as air, water, and soil. So let us go ahead and see my outline. I'm going to see some abstract. I'm going to introduce my topics. And after that, research problem and my design, my objectives, and what materials and methods are used, and what measurements are used, results and discussion, conclusion, references, and acknowledgements. That are the steps that I'm going to talk today. All right. I will try to finish my talk in limited time, so I will try to use at least 1 minute per slide as possible. So in my abstract, what I want to mention is what are really CNT and CFO can do for detecting or can be used as a sensor. CNT means carbon nanotube, and CFO are cobalt ferrite nanoparticles. So in this research, we try to monitor the magnetic properties of this compound in the dispersion of chromium and other heavy metals on them. And understanding the magnetic properties of the composite when these heavy metals are dispersed on them is the main focus of my research. Okay, so the most important parameter here using to see is the magnetization. So the magnetic properties is well monitored when the chromium is approaching the CNT-CFO. As you know, chromium is a heavy metal, does not exist as elemental level. No chromium exists in the world as elemental level. It exists as a compound. So when you go to Sigma, Aldrich, or any other places to purchase it, you can't get it, but you have to go to literature. You have to get to literature how you can obtain the best chromium hexavalent. Because as you know, chromium is a very diversified kind of ion, with it has like trivalent or hexavalent. When you see your vitamin package, you may see like your vitamin has chromium. Okay, you say like, hey, Dr. T, what are you talking about? Chromium is not toxic. It's like found in my vitamin. So this compound is very funny, and that is why our research interest. So this information will be used to develop nanosensor from that composite. What we do is we are not monitoring what happened on the chromium compound. What we monitored is what is exactly happening in the CNT-CFO composite. Okay, so let me introduce a little bit, like just run away what is like nanoscience and the nanotechnology. When there are graduate students, and I know the professors and everything, I don't need to talk to them for this because you already know about it. But so when we say nanoscience, it is the study of structures or materials in nanoscale. Nano means when you have 1 gram divided by a billion times, and that portion is 1 nano. And if you have 1 meter, and if you divided that 1 billion times, and a portion is 1 nano. So it is very, very small. That means it is this study is like electron, proton, electron, and neutron level, or elemental or molecular level. And nanotechnology is a branch of science which with dimension and tolerance of less than 100 nanometers. 100 nanometers, especially the manipulation and of individual atoms and molecules. And this is very common. Okay? We can find nanotechnology is applied in chemistry, physics, material science, molecular biology, applied mathematics, and computer science, electrical engineering, and mathematical engineering, and more. So this is what I can say about nanotechnology and the nanoscience. Carbon nanotubes. Why people are very interested now on carbon nanotubes? Okay, as I said before, when carbon reacts with oxygen, it forms carbon dioxide, and it is like it has like one global warming potential. And methane, which is carbon with hydrogen, has 21 global warming potential, and both are the contaminant, like what we call it greenhouse gases. They increase the temperature or cause something. But the carbon nanotubes, it could be multi-wall or mono-wall or di-wall. They are very important in research application because of their nanoscience, electrical conductivity, strength and elasticity, thermal conductivity, and other properties. When I was a kid, when my teachers teach me like metals are insulators, metals are conductors, and non-metals are insulators. But when you come to carbon, carbon is a non-metal, but it has a capacity of electrical conductivity. Those properties makes carbon nanotubes very important for research purpose. The others are cobalt, ferrite, nano, composite, which we call them CFOs. These are magnetic properties. These are magnetic materials. And it's made up of oxygen, cobalt, and iron. And they are coming as emerging and the most important material for research application due to their natural properties also, such as magnetic properties, electric and thermal properties, catalytic properties, and physiochemical properties. And also they are very stable. So that's why we are using these materials for our purpose. Okay, so when we think about nanosensors, we have different kind of nanosensors. Nanosensors are very small device detecting and responding to physical stimuli in a very, very small dimension, right? This can be applied in anywhere. Like we have now we have a lot of sensors in food, like there are food contaminants, biological contaminants, chemical contaminants, such as in environmental contaminants, pesticides. Okay, chemical. We do have like chemical nanosensors, and nano biosensors, nano-based sensors, now nano-wire-based sensors. There are a lot of kinds of sensors. So the sensing means when the property or the chemical or the physical property of a substance is changing in response to attachment or in response to the stimuli of the other substances. Okay. Okay. So depending on this information, we have to design research for our purpose. So my research problem and design is like, first, what are the problems? Heavy metals. Heavy metals are the major concerns in drinking water. Heavy metals have a density greater than water so that they are not dissolved in water. And heavy metals have a capacity to attach in protein or in a tissue and change the metabolism of that person. So we have the most common heavy metals: chromium, hexavalent, arsenic, cadmium, mercury, and lead. All of them have their own impact. Especially lead has a major problem in Maryland, in my town, in my area. And also chromium. Chromium exists two major forms. There are a lot of forms of chromium, but there are two major forms: chromium trivalent or chromium 3, and chromium hexavalent or chromium 6. So as you know, chromium, this is the vitamin packet. It says chromium picolinate 500 or this is 500 milligram or something like that. That means the chromium trivalent is not toxic. it can be used in our diet as a food or vitamins. But when chromium hexavalent is happening, it is very toxic, and it is very dangerous for human health. And chromium exposure is mainly from contaminated water. How? From rivers, lakes could get chromium ion contamination through erosion, through hurricane, waste products, from textile or coloring and metal industries. Chromium in industry is mainly used for shining purpose. And when you buy your Christmas decoration, when those things very shiny, make sure they don't have chromium in it. So chromium is used to make or finishing. It's painted on metal as a finishing or as coloring and make it very shiny. And this exposure can be from the industry to the soil, and that will be transported into the water sources through erosion or man-made or natural processes. So we have, I have chromium, arsenic, cadmium, mercury, lead. These are my heavy metals. And here are what are already known about them. This is from the literature. Already know about them. Let's say lead, for example, it's very dangerous for bones, liver, or kidney, lungs. Chromium here, skin, lungs, kidney, liver, brain, pancreas, testes. All these are already studied, and it causes these things. So how we can remediation, or how we can do this, or remediation process. So for the remediation process, okay, I need my cursor. We do have precipitation, absorption, bioabsorption, ion exchange, filtration, coagulation. All these they have some sort of side effect. Either they are expensive or not environmental friendly, or they are causing some secondary impacts. So science is always looking for something which is environmental friendly and cheaper and applicable to use. So that is why we are trying to use CNT and CFO as the best potential compound in developing nanosensor. And this nanosensor could detect heavy metals in trace amount below EPA standards. EPA has a limit in standards, and WHO has limit on the standard. For example, from literature, in a liter of water, it's a microgram per liter of water. For example, if microgram, for example, for lead, WHO is 10, and EPA is 0.5 microgram, okay? And for chromium, WHO is 50, and EPA is 100. So our goal is how we detect in water, in soil, in air, below the EPA and the WHO limit. So another thing that we are so interested with this is that the state of Maryland, since it's a very populous state, the geography is very small. Maryland is small, but it is most populous, or population is high in Maryland, and there are a lot of risk of contamination. And historically, when you come to chromium, chromium has been mined in Maryland. A major processor of chromium ore remained in operation until 1985 in Inner Harbor, Fells Point, Baltimore. I hope you know this. So, but we don't know which we don't know which chromium is there. But if it is from the for industrial purpose, I'm sure it's not the one which is we applied in the food, right? It should be something which is making a shiny or something like in coloring of metals. So Isaac Tyson, it's a Baltimore businessman from Baltimore, Maryland, monopoly on the world supply of chromium minerals during the mid-19th century here in Baltimore, Maryland, in our house. So probably this is a good research questions for the future, how much that soil is cleaned or how much that thing is there. Actually, there are a lot of development here. So as you can see, this picture is like before the development and this one is after the development. So I think there are a lot of changes there, but since the heavy metals stay there for longer time, so we may have some still. So that is, I am interested to do that. What other factors interesting to me? The magnetic properties. The magnetic properties, as you can see, nickel is ferromagnetic, cadmium is diamagnetic. Diamagnetics are the magnetic properties 180 degrees. That's no problem with this. Look, chromium. Chromium is antiferromagnetic. Antiferromagnetic means when you see the magnetic ordering down here for like saving my time, I'm gonna see just the antiferromagnetic orientation. Look, there is one north and one south magnetic spinning, but when you see antiferromagnetic, the two spinning are equal, so it cancels each other. So from all other heavy metals in magnetic properties, chromium has a very unique characteristics. So because of that, we designed like this. So heavy metals are coming from the environment. It could be from erosion or hurricane or from any other mechanism. So it came into here, as you can see, just source of the water. So in this source of water, as you can see, it could be a pond or river. So water, this is used to get the tap water, right? So my objective is, or my goal for the future, when we continue this work with the engineers, is to use a small device on the faucet, water faucet, so that they can detect very small amount of heavy metals before it's getting into the glass. So it comes with CFO, CNT, and then we contaminate them or disperse them with chromium or other heavy metals, and then we measure their characteristics, electromagnetic characteristics, magnetic characteristics, and all the others, or neutron scattering, or X-ray, and all that. So that information will get some sort of data, and the data will be got into data saving device. And the device send information to the computer, and the computer will tell us exactly what is that in that substance. So that is my design to do my research, okay? So I set objectives for that. The main objective of this research is, one, to develop, explain, and utilize carbon nanotube and cobalt ferrite nanocomposite as a nanomagnetic sensor for the detection of chromium in drinking water, and also to functionalize this nanocomposite as a nanomagnetic sensor for monitoring chromium in water. So it could be qualitative and it would be quantitative, okay? So what materials we used? So we do have a lot of materials we use. We purchase potassium dichromate as a source of hexavalent, carbon nanotubes, CFO nanoparticles, and we do have a lot of things. I'm not going to mention all this. So we do have different materials, and we applied all that standards of the lab procedure by different scientists to get our data, right? Then after we prepare sample in this research are categorized into 3 main groups: pristine CNT, pristine CFO, and CNTs intercalated with CFO, and also the 3 group were contaminated with chromium, hexavalent, and all that sample was going to different characterization. So chromium, potassium dichromate looks like this when it's purchased. Okay, so what is our experimental design? Experimental design, we have CNT, so characterization by vibrating sample magnetometers, scanning electron microscope, XRD, cyclic voltammetry, Raman spectroscopy, pH, small angle neutron scattering, EXAFs, all those are, by the way, that is why I'm trying to travel to different labs, state and federal labs, to get this instrumentation, because we have some of them and we don't have the others. So also the same thing for the CFO nanoparticles, and then when intercalated, make sure we don't need any chemical reaction, because chemical reaction will change the magnetic properties. Okay, so we are using a dispersion or intercalating method. And then we come with CNT CFO together and disperse it with potassium dichromate, and then characterization with all those stuff. So this is my design. Okay, so measurement is, okay, so vibrating sample magnetometer is at Morgan State University, powder X-ray diffraction at Morgan State University, and all that. These are very old and very effective methods. And the transmission electron microscope, Morgan doesn't have it, so I have to go to Joel Convention Center when they introduce their product. So I ask help, so they help me out. So they give me some data, and Raman spectroscopy measurement and SEM at Army Research Lab at Aberdeen, Maryland, and we have a beamline 3M small angle neutron scattering science at NIST, okay, Neutron Research Center for Neutron Research. And I have beamline QAS7B extended X-ray absorption fine structure EXAF at Brookhaven National Laboratory, that light source 2 in Long Island, Maryland. Long Island, New York. So I try to use those collaborations. I have a Safe Research Group. The Safe Research Group is a research group in Morgan State University who has different collaboration with different state and federal labs. So I took that advantage to do my research. All right, so what are the results? Okay, I am going good time. Okay, already 30 minutes. Okay, my results. I start with a specific M1 VSM characterization, and this is like magnetization. And we try to plot the hysteresis loop, and it's because it is a straightforward and widespread characterization of magnetic material. And this is by plotting values on flux density B against the field strength H, we can produce magnetization curve, or HF, MH curve, or more commonly known as BH curve. So we tried to see what magnetization changing as a pristine when the two intercalate and when chromium is dispersed on them. Okay, so we get result. So coefficient field is the magnitude when the loops cross the x-axis, as you know, and we take average. For CNT CFO, we have 1, and CNT CFO with potassium, it's increased to significant. And ms, electromagnetic unit per gram, this is ms means it is like saturation magnetization, and it is also shows significant increment. And mr, remnant, which is before crossing the x-axis, remnant is something before, so that also shows significant increment. So we compare that without and with chromium. And the graph and the as you can see, we tried for cadmium, lead, nickel, mercury, and this is like electromagnetic per unit or resonance magnetization and saturation magnetization. As you can see in the saturation magnetization, it is like significant increase when the that substance are contaminated or dispersed by heavy metals, chromium. Okay, so the loop shows also we have this is how the graphs looks like, and this is when that table is changed into graph. Okay, and also we compare the others together and comparison of VSM hysteresis loop of the CNT-CFO nanoparticles contaminated with cadmium, lead, nickel, and mercury. Mercury, we see a little difference, but most of them are not that much significant, but still not well studied. So our focus is only on chromium hexavalent, but still this one is still juvenile kind of report. Well, what is exactly happening in our sample when we do our intercalation and the dispersion? So to know that, we have to go ahead run XRD. So the XRD will tell us each peak, okay? And each peak will be named or coded. So the XRD peaks of CFO and CNP, CFO shows good crystal structure, and the standard magnitude of CFO's XRD pattern shows that the particles are cubic and spinel structure. And as you can see, A, B, C, so you can see all the materials peak, especially you have the CFO peak and the CFO chromium peak. And here we have CFO peaks, CR chromium peak, and CFO chromium peak. So we continue to see all parameters together. We have CNT CFO peaks, we have CFO peaks, and the CR peaks. And as you can see here, it is coming together by combining, okay? Combining the graph together. So the XRD was used for structural phase identification, and the XRD measurements indicates that the CFO magnetite was the dominant phase for the sample, which is expected. Okay. The other one is cyclic voltammetry. It's very easy, and this one is just to check if there is any chemical reaction inside our, which we don't need it, but we accomplished our goal because there is no chemical reaction. Remember, when there is chemical reaction, the reactants, when they change into products, there will be physical or chemical change. And to check that, we came up with the Nernst equation diagram. So as you can see here, these are not significant. So the cyclic voltammeter of CNT and the CFO contaminated with chromium did not show significant difference. So we try to see the individual peaks. So and in each of them, when you see that the differences are not significant, so we come to a conclusion that there was no chemical reaction between the components of the elements of the sample. So the samples are simply hooked together, they hooked together, and that the carbon nanotubes are used as a tube to transport that the the CFO materials, and the chromium are just only dispersed over them. And that is very good for VSM and also for EXAF and also for the SANS. Okay. And we try to observe in the microscope TM image of CNT here. As you can see, B is TM image of CFOs, and C is TM image of CNT CFOs with chromium. This one is just to see what this looks like. 100 nanometer, 800 nanometer, and 400 nanometer. And also we try to see electron microscopy characterization. This is also one of the characterization mechanism. So as you can see, SEM scanning electron microscope image of CNT CFO, and RHTM of image, as you can see, we have lattice fringes and also EDS. And as you can see here on D, ADS with by color, it gives by color and by element. As you can see by color, chromium is identified here. I don't know what this color looks like. It's like a gray, blue or something like that. Okay, and of course we have some sort of contamination too, because we use solvents such as like SEDS and things like that, and that contaminants also came out during this from the buffer solution or from the solvents. Okay, other one is Raman characterization. So Raman spectroscopy is a powerful method for learning the structural and active information on molecular levels. And we try to understand based on what standards we have in the Raman. This is from literature. In the literature, we have like the RBM radial, and the D band, and also the G band. So focusing on this, our sample came out. So the CNT is contaminated with chromium, indicated that the G band is, look, this is like 15,000 per centimeter. And like when you go to the Raman shift of CFO with chromium, it's shift. It's went to the 3,000. So this is a clear indication that the chromium has some sort of changing the characteristics of these two substances. Okay, so the SANS characterization, I have to go to Gettysburg, Maryland, and this is the 30-meter SANS instrument from NIST, Neutron Research. So we have sample is going here. There is 15-meter detector vessels here, 16-meter sample flight path, and there is also velocity detector. And I have to get support from the neutron scientist down there. So as you can see, sample chamber is here, and the process need about 45 to 1 hour to understand the neutron scattering of the samples. So the sample running will come to the big screen TV, and you can watch your, you can watch your sample when you have coffee in the lounge. Okay. So how SANS works? So there is unpolarized beam here, as you can see. So there are spin polarizers, and you come, the sample come here, and when the sample come here, it gives light and create angle. So when it is going to angle, there is a y-axis and the x-axis, and creates an angle. So here is where it is detected. So that is how the neutron is scattering. So it measures the patterns of neutron scattering. Okay. So raw data, the scattering patterns of the raw data indicated that the higher intensity was observed in CNTCFO, and that is like, you see that purple. And the scattering patterns of with chromium at zero gaseous has more intense than 300 gaseous. Okay, and when it is analyzed, when the data is analyzed, we come to the results that the scattering intensities are proportional to the concentration of magnetic particles. And of course, the magnetic materials already identified here, that cobalt, iron, and chromium. Okay, so we have analyzed at 0.007 Tesla and 0.07 Tesla. A is for the one contaminated with chromium, and B is for not contaminated with chromium. And as you can see on the pattern of scattering, there is huge differences in the middle spinning and middle non-spinning flip. So here around this area. Okay. So what about in 1.5 Tesla and 1.5 Tesla of the substance still with contaminated with chromium and not? So circular average scattering patterns of CNTCFO as this Tesla shows less scattering patterns of the front flip. So the front flip are here. That's the red star. So, and then when you come to the magnetic characteristics, CNT without chromium and with chromium, the magnetic scattering, a measurable signal is in remanence at 0.07 Tesla, 0.007 Tesla was observed, but 1.5 Tesla, most of the moments are presumably not that much. And in CNTCFO with chromium shows enhanced magnetism. Okay, and the non-spin flip differences in the low fields of 0.007 Tesla shows big differences in the field. So we come to the most obvious differences between the samples is that the CNTCFO chromium is harder to saturate than CNTCFO without chromium. So our goal is, our hypothesis is supported by the result. So we come to the conclusion that the magnetic scattering at 0.07 Tesla and 1.5 Tesla on CNTCFO with and without chromium showed differences. And as you know, we came up with the difference in magnetic moment is about 33.3% when it's contaminated with chromium. So that is the result from the science. Okay, and the other one is the last one is okay. I have okay. How many? I don't know how many minutes I have. So so the beamline QS7B at Brookhaven National Laboratory down there in New York is I was supported by Dr. Sayed, and this is also another way to determine what is exactly happening in this compound. We prepare sample, and this is a pattern, and this is a sample running. So from the data, as you see, different energies are required to remove iron and chromium. Of course, this is like, of course, this is known. So this is like a great thing that we move to the B. So when we go to the B, the wave vector of iron in the composite exhibit difference energy with and without chromium, because we can't get the wave vector of chromium because chromium can't exist by itself. So we are using the iron. So So the iron can be used as reference what is exactly happening for chromium. Number C, as you can see, there is a fundamental difference in the radial distance between CNT and the CFO. Okay, so we came to conclusion for the entire research. After collecting all data from VSM, from all those sands and exafs, we come to conclusions that magnetic measurement revealed significant change in remnant and saturation of these substances, okay, when they are contaminated with chromium, and in a very minute amount. Remember, we used a very small. And VSM analysis indicates that the saturation magnetization of the composite increased by 40 electromagnetic units per gram electromagnetic per gram of sample. Okay, and about this is like 71.5 increments in magnetization. So the CNT-CFO responded to chromium significantly, and the SANS investigation indicates that the net moment about the is about 33.3 magnetic enhancement has recorded. And for this information, we can conclude that the CNT-CFO nanocomposite can specifically detect the metal chromium and be used as a potential magnetic nanosensor for chromium. So how can we add? This is a potential, this is the knowledge here, but an engineer or somebody who supports this will change to something usable for public. And it's very easy too. I used more than 150 references to do my research. And I do have acknowledgements for my advisor, Dr. Daraje Saifu, physics department at Morgan State University. And Morgan State University helped me, a lot of people helped me, the dean, I was funded, I didn't pay any tuition, and I was paid 20 hours and working in the lab. That is a good thing. And so for that reason, I can thank you for physics department, chemistry and the biology department. And from Army Research Lab, Appalachian Maryland, Dr. Shashi Karma, Dan L. Choi, and from National Light Source 2 at Brookhaven National Laboratory, Dr. Said and Dr. Steven, and at NIST, Neutral Research, Dr. Catherine and Dr. Paul, and external labs, Army Research Lab, Brookhaven National Laboratory, and NIST. I would like to thank you all to help me out. And thank you very much for listening to me. I'm sure you hear me, even if I have some accent. I think my voice is very hearable. So I have dissertation committee here, which I forget. These are my dissertation committee members. And thank you for all, and thank you for listening. If you have any questions, I am ready to take. I'm sure, I don't know, I used my time properly. I think it's like 4:30 will be the end, right?
Thank you very much, Tassew. I think, yeah, I think you used your time well. We've got definitely plenty of time for questions. So I'll kind of, again, you know, you can either sort of put your question in the chat if you'd like me to read it off, or it's a small group, so feel free to chime in.
Okay, we'll try my best.
Tassew, I have a quick question. It's not, you know, it's not so much related to the research in terms of detecting chromium per se, but I was just kind of curious. You mentioned how, you know, reduced chromium is kind of like essential, right? It comes in vitamins and such, and so it plays a role in the body. But the oxidized hexavalent chromium is toxic. I was just kind of wondering. So part of your talk here was about how certain areas of Maryland might have considerable contamination, and you'd want to figure out which, you know, the chromium contamination level, but also which type of chromium. If you, for example, had significant exposure to reduced chromium, given the oxidation that occurs in biological systems, would that be a risk in terms of, consuming the type of chromium that's not toxic and having that be reduced like in a biological system, for example?
If I got your question, if it is try to reduce the hexavalent down to trivalent by any mechanism or some sort of, which I don't know for sure. The literature is saying that the hexavalent is considered like heavy metal. So it causes, so if you consume hexavalent and try to reduce down by some sort of mechanism, I don't know, to be honest with you. It's not well studied.
And you know what? I just realized I'm explaining it backwards. If it's the, so it's actually the it's actually the other way around. That sorry, if you can bear with me. It's been a while since I've taken inorganic chemistry, but it's the other way around. So like you want the reduced form and not the oxidized form, right? Now I'm having a hard time thinking about it even.
Yeah. Of course, yeah.
All right, so yeah, so in any case, it sounds like
yes.
Not a clear answer. Well, thank you for your talk. I really enjoyed it.
Okay, thank you so much.
I had a different question, Rodney. Again, I don't do very much with heavy metals, but we have been measuring chromium, lead, zinc, cadmium, and some other things in stormwater in Maryland. And to be honest, we really don't see very high dissolved concentrations, even in urban stormwater, which is kind of interesting. And the interpretation we have tentatively is there just really isn't a major source of these metals, in the places we're working. I mean, there's not, unless you're mining it and have tailing wastes or something like that, there doesn't seem to be any obvious sources aside from, I guess, the one you mentioned in Baltimore. But my question is this: with lead, we do know that there is a problem, a fairly urgent problem in drinking water contamination. And of course, it's related to lead in old plumbing systems in our older cities. And I'm just wondering this: why, do you feel like the focus on chromium is as important as the focus we might have on lead? And secondly, are there people working on the same kind of technology that would help us address lead, in drinking water, particularly in old urban systems at the same time? Are people doing that, or could your technique be modified to work on that problem as well?
That is very interesting. The reason we try to shift to chromium is, one, chromium is less studied.
Sure.
When you go to literature, chromium is less studied.
Yep.
And also people didn't realize the impacts of chromium. And also chromium is very beautiful. Probably you may have one substance in your kitchen.
Yeah.
Or somewhere. So
sure.
That is one reason. And the other reason is this CNT and CFO, especially like CFO, it's magnetic nanoparticles. So the magnetic information of each metal is a factor to choose for the chromium. And when you come to the lead, we do have tons of millions of research done on the lead, and the problem is known. And we have lead detector. Even like you can hire like a company who detect lead in your house. So that is why we are like concentrated to the lead side. But
Okay,
still
so-
there is
yeah.
a research team who tried to see the lead concentration of the soil where these houses are demolished from Baltimore area, that's the right term to use, demolished. But I don't know how much they move forward. And in Morgan State, we have the different research team. And I don't know how much that safe research group will be extended to the lead, but there are some other research team working on that too. That is why I want to concentrate on that lead.
Okay, that makes sense.
Yeah. Yeah.
Thank you. Thanks.
Thank you so much. Any other question?
All right, well, there's a few more minutes if anybody wants to chime in. I did notice you got several thank yous in the chat. People enjoyed the talk, and so just once again, thanks for joining us here today, and wish you all the best of luck in your continued research endeavors.
Thank you so much, and I think I will be available tomorrow somewhere. I don't know what time. It's what.
Yeah, that's correct. I think that Rhonda's worked on setting up a number of meetings in the morning, so I'll be chatting with you tomorrow morning.
All right, so you're gonna email to me, right? Yeah, okay.
I don't know if Rhonda's still on, but I hope so.
Yes, I am. I will send you, after the seminar today, I will send you the information for tomorrow's meetings.
Okay, thank you so much.
You are very welcome.
Okay. All right.
Okay, take care, everyone.
Take care. Bye.
Thank you.
Thank you.